right, ladies and gentlemen, welcome back for another round. This is Mr. Doolin. Thank you so much for tuning in. Today what we're going to do is we're going to take a look at ionic formula writing. So this is a continuation on all of the ionic formula writing that we've done so far. We've looked at main group elements, we've looked at ionic formula writing with transition metals, and then today we're going to add just another little quirk to it, and we're going to throw in some polyatomic ions, all right? And so a polyatomic ion, what it actually is, it's a covalent molecule with an overall ionic charge. And so that's definitely something you will want to know, right? A polyatomic ion is a covalent molecule with an overall ionic charge. And the reason that becomes important is because since it has an overall ionic charge, the ion itself will participate in ionic bonding, and it will be either the cation or the anion in the particular ionic bond. So what I'm going to do is I'm actually going to give you a list of polyatomic ions I want you to memorize. All right, and so just like magic, I've popped a lot of these up on the screen, and you're probably a little overwhelmed if you're looking at this. But a lot of these we've seen before when we were drawing our covalent Lewis dot structures. I gave you a lot of these to actually draw in that particular unit. And I've got a couple of divisions here that I want to go through with you. But before we do that, let's take a look and make sure that we understand what we need to get down and what we're going to be held responsible for. All right, so you will definitely need to know the formula. All right, so NH4 is the formula of ammonium, right? The charge up top, the number up top, whether it's a positive or a negative number, is the overall charge of the polyatomic ion, and you will need to know that as well. And then also you'll be responsible for the name. So you have to know name, formula, and charge for all of these polyatomic ions. You're not going to be given a list or a bank of these, all right? It's just something that you're going to have to know. So now let's use a couple of memory tricks. Let's make it easy on ourselves. The first one, ammonium, the one I'm looking at here, NH4+, that is our only positive polyatomic ion that we are going to deal with, all right? And so it will serve as the cation in the particular ionic compound, i.e. it will be listed first, okay? The second set here that I've got, acetate, hydroxide, oxalate, and chromate, they are our odd ducks. And by odd ducks, I mean, you know, like if I look at acetate, it's more than one. It doesn't have a main central atom. Hydroxide, same thing. Oxalate, same thing. And then chromate, I put in the odd duck category because it doesn't follow some of the naming pattern rules that we're going to look at for the rest of them. All right? So the second column would be our odd ducks, right? They don't follow our naming rules for polyatomic ions. But these over here, right? These will actually follow a naming and formula pattern based on the number of oxygens present. Well, you need to know the 8s, and so chlorate, manganate, nitrate, bromate, iodate, carbonate, sulfate, and phosphate. You'll need to know them, names, formulas, charges, all right? And then I'm going to teach you a naming pattern so that you don't have to memorize like 50 of these. You only have to memorize the ones that I've got on the screen here, okay? Okay, and so what I've got here is I've actually erased the screen and just listed the naming patterns. I'd suggest that you pause for a second, get this down real quick so you can listen to me as I'm talking about it, all right? Okay, and so the ones that we're going to look at and memorize is we're actually going to memorize the ATE polyatomic, so the nitrate, the carbonate, the sulfate. So these ATE endings, right, we memorize them because they are the most abundant or most common polyatomic ions. So most abundant or most common. Those are the ones that we're going to memorize. And then everything else in this naming pattern is going to be based on there. Now, what we do is the most abundant is going to tell us the number of oxygens. It's going to be our relative starting point for the number of oxygens present in all of the rest of them. All right? So what we do is we go to the ITE form, and this has one less oxygen than the ATE polyatomic form. And so if you're looking at your list, carbonate would have 3 oxygens, carbonite would have 2 oxygens, all right? And then the hypoite has 2 less oxygens than the ATE polyatomic. And then when I jump up above 8, I have the PreAP, and what this has is it has 1 more oxygen than the ATE form. And so now you know why we memorize the ATE form is because the naming patterns are all based on the relative number of oxygens in comparison to the ATE form. All right? Okay, and so I'm going to do an example here with you. Okay, and so what I've got written on the screen here is chlorate. And now what we're going to do is we're going to run through the ites, the hypoites, and the per-ates, okay? And so if I'm going to say, hey, I've got chlorite, then if I look at my naming pattern, then I know that all I've got is one less oxygen than the ATE, so I would come over here and I'd write it as ClO2. It still stays a negative charge. The polyatomic ion families here that we're going to be naming, the charges will not change. The charges will not change. It's only the number of oxygens that changes inside of this naming pattern. That is a very important distinction. I know it seems simple, but very important to keep straight in your head. All right. Now the next one we'll take a look at is we will look at the hypochlorite. And what that tells me is that there are now two less oxygens. And so I've just got ClO minus, because now I've got two less oxygens in the ATE form. And so you see that line that I gave you in the naming is just the root of the polyatomic itself. All right. So hypochlorite. All right. And then what we're going to do is now we're going to look above and we will go to perchlorate. So perchlorate, and again, it's all relative to the number of oxygens, so that would be ClO4 minus. And again, charge does not change. It's just the ending of the name changes, and that's telling me how many oxygens are there relative to the ATE form that I actually have embedded in my head. All right? All right, folks, so what I want to do now is I just want to run through with you a couple of really quick examples. So my first one I've got is sodium acetate. All right? And so notice now I'm keying in on this ATE ending. It's not the IDE, ladies and gentlemen. Remember, IDE signifies it is an element from the periodic table. This is an ATE ending. It tells me it is not an element from the periodic table. Now I know I'm looking at a polyatomic. So those endings are key for us when we're looking at a particular name. So now all I'm doing is going through the same routine. I've got sodium. I've memorized acetate. So it's C2H3O2 with a -1 charge. I look at the periodic table. I see that sodium has a +1 because it's a group 1 metal. All right. And now I'm just balancing charges just like I've been doing. And I see a +1, -1. I know that it's balanced. I should have one of each of those. So I would just write it as sodium with acetate. Right? Simple enough. Now, aluminum sulfate. Let's go through that. So again, I'm keying on the ATE ending. I know that I've got a polyatomic there. I've got it logged in my brain as to what it is, and that is SO4 -2. I know aluminum off of the periodic table is aluminum with a +3, and I understand, I know I made the assumption here, ladies and gentlemen, that you knew that this was an ionic compound, right, because it's got a metal there. So I've got aluminum as sulfate. Now I'm going to balance out these charges. And so this is why the shortcut method kind of confuses us sometimes when we start getting to these polyatomics. So now I see I've got a net +3 -2. I know my least common multiple there is 6. So I'm going to multiply. I need 2 of those, and I need 3 of those. So when I come over here, I'm going to write Al2, but now I can't change this subscript, because if I change it to something different, it's no longer sulfate. So sulfate is SO4. I cannot change that, but I need 3 of them. And so what I will do is I will put a polyatomic that I need more than one of. I will put it in parentheses and put my subscript outside the parentheses. And what that tells me is I have 3 sulfates here. All right? And so we never, when we're writing our formulas, we will never change the subscripts on the polyatomics, because you just saw the naming patterns there, right? If we change the subscripts, then we change the polyatomic itself. It's not what we actually started with anymore, okay? And if we have more than one polyatomic, we will put it in parentheses. So make sure that you get that down in your notes as well. All right? Okay, I know I said a second ago that we were going to jump on in, and if you had questions, I'd see you in class, but now here's the real deal. I decided to come back and add some examples here. So if you have questions, I'll see you in tutorials, and otherwise I'll see you in class, ladies and gentlemen.